Okay friends, good morning and welcome to this lecture series of geomorphology, and today we are going to discuss different factors and different regions for weathering and erosion. If you remember your last class, we were talking about this mechanical weathering or physical weathering, and the reason was the pressure unloading as well as growth of foreign crystals. So, if we resume it within 2 minutes or so, pressure unloading that was mostly responsible for exfoliations. That means, if you are removing the overburden pressure, the rocks in the depth which was formed, they are unpressurized or depressurized, and finally, spalls of rocks comes out at layers, and those layers are mostly parallel to the topography. These were the main reason for weathering of granite and massive quartzite. And similarly, there was foreign crystal growth. Foreign crystals mostly we are talking about the growth of ice crystals and growth of pyrite. So, if you remember precisely, the permafrost region, the higher reaches and higher altitudes, mostly the rocks are eroded by the growth of the ice sheets or these ice crystals within these rock fractures. Similarly, in shales and other types of rocks, the growth of pyrite, it is an exothermic reaction, and finally, it reacts with oxygen and forms smokes. So, that is why smoking hills that we are discussing in the last class. In the present class, we will discuss another factors which are mostly responsible for this physical weathering and some of this chemical weathering also. So, here the prominent factor we are going to discuss about the thermal expansion and contraction. Generally, this thermal expansion and contraction, these are mostly active in the high temperate regions like the deserts, and if you believe me, it is in moon too, lunar erosion. So, boulders and cobbles exposed to hot desert sun and are found broken somewhat orange slices. This is due to thermal expansion. So, it is very interesting fact to note here that in desert travelers in Saharas, they were listening the rifle shot sound during the evening time when they were moving through this desert. This is due to this expansion and contraction of these rocks or the boulders in the Sahara, where the daytime temperature was very high and this nighttime temperature also reduces. So, that this thermal expansion during the daytime and contraction in the evening time, they are creating stress, that means expansion and contraction of these boulders and the upper surface. And if you analyze it very precisely, that this expansion and contraction is not uniform throughout. If you remain yourself on the surface of a boulder, so here the temperature effect is more as compared to the inner part. So, that is why the upper surface of this boulder it expands at higher rate as compared to the inner side of this boulder. Similarly, at the evening time, due to fall of temperature, this it contracts, and alternative expansion and contraction creates minute cracks, and those cracks are responsible for weathering or physical breaking down of those boulders in the Sahara deserts. Generally, differential expansion also in the some rocks, or even if every rock, there are differential expansion occurs due to heating and thawing. How it happens so? We know that these rocks that is mostly composed of minerals of different kind. There are also monomineralic rock like dewnite, peridotite, these are the monomineralic rock. However, once we say it is monomineralic, that does not mean it is 100% composed of that mineral, but it matters. We are talking about these rocks which are composed of different types of minerals. For example, take granite. Granite, it is composed of mostly quartz and feldspars, is not it? So, if you put this granite block in a temperate environment, the quartz expansion and contraction will be different as compared to the feldspar. So, some of these minerals like quartz, it expands 3 times more than the feldspars. So, now imagine a block is composed of granite, we have quartz and we have feldspar and we heat it. So, the quartz will expand. However, at this as compared to the feldspar, the quartz is expanding at a higher rate as compared to the feldspar. So, that what happens within that mineral, within that quartz, suppose this is a quartz crystal, within that quartz crystal their expansion will be different. Similarly, once it expands and feldspar is here, so there will be friction between this quartz and feldspar boundary. So, that means within a mineral there will be differential expansion, there will be stress within that mineral, there will be stress intermineral space like the quartz and feldspar along these walls there will be differential stresses. In addition, quartz and feldspar, many other common minerals also expand under heat and highly anisotropic fashions. So, this type of differential expansion relates to development of cracks in the rock. In this figure given here, if you see here, confront yourself, this cold quartz if you see, this axis is this much. However, if it is warm quartz, if you see, this axis is different, and if you take a cross section, here you see these quartz crystals, these atoms, they are arranged in this fashion. However, this is in elliptical fashion. Why? This is due to expansion due to heating. So, that means this type of differential expansion that creates cracks among these mineral walls, among the mineral junctions. So, it has been noticed some of the minerals they expand 20 times greater than others along their axis. So, those type of minerals which expands and contracts more, they are prone to weathering much faster as compared to the other part. So, in a rock block, if it is composed of this type of mineral having anisotropic characteristics, those rocks will be more prone to weathering as compared to the rocks which is composed of like this monomineralic rock as compared to monomineralic rock. So, this type of thermal expansion and contraction, it is a prominent region of weathering on lunar surface, because we know this moon we do not have water there at present, and in moon we do not have air, we do not have rivers, we do not have oceans, do not have glaciers, is not it. So, and second thing is that we do not have tectonic process evidences, we do not have evidences of a tectonic process working on the lunar surface. And second thing that as it has no atmosphere at present, so sun rays can directly hit the rock surface on the moon. That is why the weathering of lunar surface or the moon, it is totally different than the weathering on the earth surface. So, that is why this thermal expansion and contraction, it is thought to be the playing prominent role in weathering or the physical weathering in the lunar surface. And ground temperature in hot deserts exceeds 85 degree in diurnal fluctuation greater than 50 degree. So, now you see if in the figure if you concentrate here, this is outgoing terrestrial radiation and this is the temperature where solar radiation is there. So, finally, by reducing those we are getting the net gain of temperature this much. So, if this happens, so a rock body which is accumulating this much heat, that means it under expansion, that means under tension. So, this type of tension is mostly responsible for development of cracks on the rock surface, and therefore, these hot desert rocks, they are more prone to weathering by this thermal expansion and contraction. Why? If you see here, because heating decreases rapidly with depth. During daytime, outer few centimeters of the rock expand relative to this deeper part. However, as the outer shell cools, it contracts faster than also in the inner part. This type of differential expansion and contraction is responsible for development of cracks, because alternating we are compressing it and extending it. In the night time we are compressing the system, we are cooling the system, we are allowed to compress, but in the daytime we are expanding the system, because we are putting heat and finally rock surface is expanding. So, during daytime expansion and night time compaction, this is mostly responsible for development of cracks on the rock body. Then whenever we talk about this thermal expansion, we are always talking about this the hot area or hot deserts or these moons like it. But there are cold deserts also, because we know there are two types of desert existing on the earth surface. One is called low latitude deserts. Low latitude desert means it is remain from 0 degree or from the equator to 30 degree. In this area there are called low latitude deserts. Mostly these are the hot deserts. If you see here, these Saharas, Kalaharis, the Thar deserts, all Indian context, if we see the Thar deserts, all are the low latitude deserts, they are very hot. So, other type of deserts, they are called cold deserts. Cold deserts, they are mostly in the higher latitudes like the Antarctic ice sheet, the Arctic, these are called the cold deserts. So, irrespective of this hot and cold desert, the thermal expansion is there, and even in cold deserts the thermal expansion is more pronounced, because in most of this time they remains in the cool condition, and once there is some sun rays that is hitting the surface, this rate of cooling is much fast as compared to this rate of expansion. So, that is why this rock surface on these cold deserts, they expand more as compared to, they respond more as compared to these rocks of these hot deserts. So, thermal effects are not limited to low latitude deserts, they are even more pronounced in the regions of extremely low air temperature such as Antarctica. So, that means I want to say the thermal expansion and contraction, this phenomenon is not only restricted to this lower part or the lower deserts or the low latitude area, that can also be felt in high latitude areas. Then another factor of thermal expansion and contraction is due to forest fire, because you know many square kilometers of the forest we are losing every year due to the forest fire, and thermal shock generated by bush fire and forest fire has been observed to spall 5 to 50%, even 70 to 90% rock surface or the boulder surface in the forest. It expands and contracts. During this forest fire, the rock expands and finally cracking takes place, and we have felt that that rifle, like this rifle shot sounds during our field work when we are in Geological Survey of India. There are forest fires, and finally the forest, these boulders, they were cracking like creating some sound similar as to this rifle shot. So, spalls ranging from few millimeters to few centimeters remove areas of several hundreds of centimeter square of boulders, and mostly in their sides. So, that means this forest fire gradually reduces the boulder size, because it removes layers of these rocks due to this thermal expansion and cracking. Then here there is a culprit which is called water. This is mostly responsible for rock surface weathering. Because if you see water in pore space and fracture has an important but variable influence on fire spalling. Water plays major role in spalling of boulders during forest fire. It has two roles. What? One is, on one hand, by boiling away it can delay and reduce the heating of this rock. Water, once there is water which is confined within rocks and forest fire takes place. So, water starts boiling. Once water starts to boiling, it will reduce the temperature, it will delay the rock to expand. In the other hand, the steam can be a potent mechanical and chemical reactant. The steam which is created, it is mechanical and chemical reactant to fracture the rocks, because it is expanding, it has to move up. So, the pore spaces of the rock, if it is water is there, so it is heated up, the water will try to convert to steam and it is to move up. So, it is to expand. Once it expands, that means it increases pore pressures. So, due to this increment of pore pressure, these rocks are cracked. And finally, and second thing, that water behaves as a reagent to chemically transport salts from one place to another place. This also one reason for chemical weathering we will discuss in later classes. Then whatever we are talking so far, it is due to pressure unloading, due to development or due to growth of foreign crystal, due to thermal expansion and contraction. These all are related to mechanical weathering or physical weathering. So, now onward we are going to discuss about chemical weathering. So, in the initial classes, when we are talking something about the difference between physical and chemical weathering, you can remember that physical weathering is simply breaking down of rocks without change of its chemical composition. However, the chemical weathering is concerned, its chemical composition of the rock changes, its product is different. In physical weathering, quartzite will produce quartzite, but its chemical weathering, quartzite will not produce quartzite, it will quartz and some liquid or some fluid. So, that means I want to say in chemical weathering we get a product which is compositionally different from its parent rock. So, this is called chemical weathering. When the rock that weather change their composition into a new type of rock, this is referred to as chemical weathering. For example, if limestone is there, limestone mostly composed of calcite. So, it dissolves as a result of acid rain, then it becomes carbon dioxide and various ion. So, that means here you see the product we are getting, it is totally different from this surrounding or from the parent rock. So, this is chemical weathering. If we distinguish physical or mechanical weathering is generally credited with being 6 times more effective than the chemical weathering. Though we have weatherings of 3 types, but this physical weathering, it plays prominent role in reshaping the earth crust. Most part of this earth surface area is affected by physical weathering, and that is why it says it 6 times more effective than the chemical weathering. But through the earth's geological history, if you remember, the chemical weathering has played as major role in ocean atmospheric, biospheric, lithospheric system, maintaining atmospheric oxygen and CO2 content at the global temperature within narrow limit. So, that means this oxygen, supplying oxygen to the atmosphere, this water, formation of water, those have played, chemical weathering has played major role. However, physical weathering, it has simply broke down the surface, but chemical weathering, this global atmospheric pressure, global atmospheric composition, global ocean water EH pH condition, those were maintained due to this chemical weathering. in this figure if you see, suppose we have a hill and half part we allow it for physical weathering and half part we allow for chemical weathering. What we are getting here? By weathering, physical weathering, we are getting sand, silt, clay, that means fragments, clastics, clastic and non-clastic. Clastic means we have clasts, we have fragments, some sand, silt, clay, those are the clastics, and non-clastics, that means we cannot distinguish grains like limestone, dolomite, they are non-clastic rocks, shale, sandstone, they are clastic rocks. So, if we allow it for physical weathering, from this hill we will get boulders, pebbles, cobbles, sand, silt, clay, that means fragments we are generating. But if we concentrate our in the chemical part, we are getting clays, they are clays. So, that means here no fragments, only chemically precipitates. So, that means physical weathering, one part is giving us grains or clasts, chemical weathering it is chemically precipitates. Okay. Physical versus chemical weathering, if you concentrate here, physical weathering refers to the disintegration and disaggregation of rocks by physical breaking down apart. Chemical weathering refers to decomposition of rocks and minerals as chemical reactions alter them into new substances. So, this is the basic difference between physical and chemical weathering. Now, physical weathering, erosion, new surface, finally you see earlier this was the rock block and due to physical weathering these cracks are developed, finally these are these boulders we are getting down. When chemical weathering, you see these were the hills and finally we are getting chemically altered product. Chemically altered product, it will be different composition as compared to this hill is concerned. And here physical weathering processes and pressure applied, freezing, and here the pressure is 200 megapascal, crystallization, hydration of salt, clay expansion. So, these are this pressure related for each of these corresponding processes. Process and effect, differential thermal expansion and insulation, pressure unloading, joints is formed, wet and dry expansion, similarly incipient fracture open, freezing and thawing, disintegration rock. So, that means already we have discussed those things. That means physical processes are there and the products are there, chemical processes will be there and its products will be there. So, total different system. Okay. Now, the question arises, if this chemical weathering is there, then where it starts and where it ends. In the earlier classes I have told you this weathering and erosion process, it starts from microparticles, nano levels, and it may goes up to the regional scale. Similarly, this chemical process also, it starts from micro and nano levels, it is from crystal levels, from this cleavage level and there is crystal discontinuities level, and it is moves to the regional level too. So, if you see here, this is a photomicrograph of some rocks, these are the altered products, these are the altered products. That means, these mineral constituents of these rocks, they are chemically altered and chemically alteration product is the clay product, is the clay. So, that means, this chemical weathering, it starts from mineral crystal lattice. These are these sites, mineral dislocation. If you see here, an important principle of chemical weathering that mineral dissolution is concentrated along sites of excess surface energy. This is very important to understand. These sites, it starts from the sites of accumulation of excess surface energy. What are those? Those are generally the crystal dislocations, cleavage planes, micro cracks and other imperfections. So, during crystallization we have crystal imperfections, like this crystal dislocation will be there, like the cleavage will be there, some micro cracks are later developed also. So, those are the sites for energy storage, maximum surface energy is stored in those sites. So, those are the sites for alteration fast. So, that is why if a mineral is placed in a chemically active environment, those sites will react fast to this chemical compound, chemical reactions, these sites will take part fast, and finally, it will produce some chemically that means weathered products. Chemical weathering is governed by kinetics of these chemical reactions, and these activated sites are mineral surface and not by diffusion rate. So, those sites first takes place in chemical reactions, and let us see what is their products. Mostly the chemical weathering, the product is the clay. To what extent this chemical reaction will continue and to what rate it will continue. So, that means a rock, whether it is prone to weather at what rate, whether the rock will weather very fast or this rate of chemical weathering, or the rock will weather very slowly, at what rate the chemical reaction will go on, that depends upon the equilibrium and disequilibrium. If rapid disequilibrium exists between the reactant and the products, then this chemical reaction will continue very fast. So, but if it equilibrium occurs, then it is very slow or it will not work at all. So, that means if the reactant are not renewed and equilibrium is approached, the reaction will slow down. So, a rock will chemically weather fast or slow, that depends upon the process. Okay. So, two types of chemical weathering we can expect, one is congruent weathering, another is incongruent weathering. Congruent weathering means a rock which is getting weathered uniformly. That means dissolution can be either congruent, in which the components of the solid are equally soluble and occurs in the solution in the same proportion as in the solid. This is called congruent chemical reactions. And incongruent, if certain soluble is a different component go in solution and other remains in the solid, this is incongruent relation. So, in that case, in the second case incongruent relation, we are getting some residual product, residual weathering, that is called residual product or residual weathering. So, generally due to this residual weathering, incongruent melting, incongruent chemical reaction, some of these valuable minerals we can able to extract nowadays. The best example is your bauxite. This is due to residual chemical reaction, residual weathering, residual product is there, it is bauxite. All other remains in the solution and finally it is removed, but this aluminum remains inside, aluminum enriched at the site. So, that is why in the Deccan basalt, in Eastern Ghat mobile belts, we will get bauxite deposit, which are the example of residual weathering and residual accumulation. This is due to incongruent reactions in chemical weathering. So, for the incongruent or the congruent, whatever may be, due to this, for this chemical weathering, water also plays major role. If you remember in physical weathering, when we talk about this hot water response role of water in thermal expansion and contraction in forest fire, related to forest fire and the rock in the pore spaces due to heating and thawing process, there also water played major role. Similarly, in chemical weathering, water plays very important role to distribute these products, to react with these constituents. And now the question arises, how water works. Here water in rocks, they present in four forms. First is your chemically combined water. Chemically combined water, that means water remains in the mineral lattice itself, mineral structure itself. What is gypsum? It is Mg, magnesium and water, calcium, magnesium and water. Similarly, mulunite, it is a copper oxide, or copper hydroxide, that means water is there. Then clay minerals, we have water in their interlayer spaces, we have two types of clay, TOT, that means sorry two types of tetrahedron, octahedron, tetrahedron. So, here water remains within this crystal lattice, crystal structure. So, in all those minerals, either it is gypsum or mullite or clay minerals, water remains in the crystal structures. It is inherent property of the mineral, they need water to form this crystals. Second type of water, it is hygroscopic water. That means, due to water's adhesive force, thin film of water, thin film, you cannot see in your naked eye, thin film, that means 0.01 millimeter or so or less than that, that remains on the boulder surface, they remains on the rock surface. Here if you see in this figure, this is the water which is surrounding the boulder, that is called hygroscopic water. With the density and viscosity much greater than the normal and not mobile under gravity. This water will not move under the gravity, but if water remains free, so if we tilt it, water will move towards a lower slope. But these are the hygroscopic water, they remains intact on this rock surface, that will not move in terms of gravity. Third type of water present is called capillary water. We know within that pore space, due to capillary force, the water remains inside. And fourth is gravity water, that is free water that moves through larger pores and cracks under the gravity and other pressure gradient. So, these four type of water, they all play role in terms of chemical weathering. Each of this water facilitate weathering in a variety of way. What are the different type of ways the water plays a role in weathering? First and foremost is as a transport medium for reactants and solutes. It is a transport medium, though pore spaces is water is there, it reacts with these rocks and this product, some of the soluble products it transports through these pores from one place to another. During transportation, it will interact with the surrounding rock, and if this if the liquid is reactive to this surrounding rocks, then again it will promote chemical weathering in the surrounding. So, during transportation, it transports the products and transports the solutes from one place to another. During transportation, it reacts with the surrounding rock. As a solvent, by exerting mechanical pressure, pore pressure, mechanical pressure means pore pressure increases, pore pressure increases means it cracks rocks. As a chemical reactant, it works as a chemical reactant, and fourth is as a chemical buffer. So, all these four A, B, C, D, all the four procedures are there, how water is working as an active role, water is playing as an active role for chemical reactions. Chemical processes are exothermic and it produces less dense material with high volume, more voluminous material are there. If you remember our physical weathering class, when we are talking about the pyrite oxidation and formation of pyrite, that also that means these chemical reactions, they are exothermic, it increases heat, it produces heat, that is why we are talking about the smoking hill. Similarly, here in the chemical products are voluminous material, less dense material. So, inside the rock pore spaces, if the chemical reaction occurs, so volume whatever the product will be there of more volume. So, to occupy that volume, the rock has to expand. So, pore pressure increases. So, that is why rocks getting cracked. So, these are the few figures are here. In this last figure, if you see, this is the iron chain and it is oxidized. Finally, you see this thickness increased, it is swelled off. Similarly, this is a chemical weathering here, see differential weathering is there. Finally, this is weathered and this shape of this statue is like that. And this is very prominent type of chemical weathering of limestone. Chemically weathered materials are removed and somewhere deposited in terms of clay. and the surface is looking like this. So, water plays major role in chemical weathering. Experiment carried out by this gentleman J. H. Faith in 1964 suggesting a rapid reaction of water by tracing dissolved material in it. How? There are 3 points he noted. The fresh snow has dissolved material in few ppm consisting of CO2, NaCl and dust material. As snow melt water is soaked in soil, mineral content increases 7.5 times. After few months or few years, this mineral content is doubled. So, that means how is water is absorbed in rocks, in slow melt water particularly, how they try to change the rock composition, the soil composition. This is a classic example of chemical weathering. Then another type of chemical weathering is, and the most important type is the oxidation. Oxidation always takes place with the presence of water, that is rusting of iron. Oxidation, oxygen is involved here. It is a typical type of weathering with increased volume, reactions between mineral and wet atmosphere. And if you see here 2 figures are there, first figure we have discussed, this is the oxidation of iron. Similarly, here this red color of rocks, the red color rocks, it is due to mineral oxidation. Even if 1% iron if there in a rock, in a sedimentary rock, in any rock, 1% iron is there, it will create whole rock red. We have red beds, we have oxidized sediments, we have sandstones, there is totally red color, this is due to oxidation. But mind it, if we have igneous rock and sedimentary rock together, both contain same percentage of iron, this sedimentary rock will react very fast as compared to this igneous rocks. That means, reaction will be same, but the rate of spreading of this red color, because sedimentary rocks are porous and permeable, it will allow this water to pass. Again water comes here, that means water plays major role in chemical weathering. So, if rock is porous and permeable, and due to this chemical reaction, this water will move fast within the pore spaces, and finally, the whole rock will create red color. So, the red sandstone, these are the products of oxidation. Reduction of iron to ferrous state takes place by some organic process in stagnant water. It imparts grey and dark grey color to the sediments and results deposition of foul sediment on organic rich mud. We have this type of colored sediments, nowadays it is very well exposed. So, this is due to the oxidation, and due to this oxidation there are many mineral deposits we get nowadays. In the Precambrian time there was oxidation, huge oxidized environment was occurred some point of geological times. These iron deposits, these are the products of oxidations. Oxidation reduction reactions are inevitable, with the result that instead of mineral going into hydrous solution as a ionic species, new compounds are formed, some are not soluble or insoluble. And oxidation, it mostly effective in a moist environment, humid environment as compared to dry environment. There are examples in the most dry environment in Saharas, in Kalahari's. There were equipments, abandoned equipments still lying, which is unaffected by oxidation due to deficiency of moisture, deficiency of water. So, that is when it again it gives another example that presence of water, the reaction is more as compared to this deficiency of water. So, if water is there in the atmosphere, that will oxidize the iron very fast as compared to the dry air. So, here this example is quoted: unprotected iron surface take clean and bright in extremely dry air, as it is proved by the conditions of tools and equipments found in polar region or in the Libyan desert decades after they were abandoned. So, that remain as it is. However, this moist environment, the humid environment, these equipments reacts fast with the atmosphere, and finally, it creates this oxidized product, and it rust very fast. So, this is this end of the story. So, thank you very much. We will meet in the next class.